Hey everyone, welcome back to 3 Deviations. In today's video, we are going to get into one of the more conceptually difficult topics of the course, or of the unit at least, to round off our study of the gradient and the directional derivative. Now, what's important here that we're going to learn is that, again, 3D functions functions with 3D inputs are very hard to visualize. And that's what really makes this a super hard topic, because we need to think about three-dimensional input spaces with a one-dimensional output. So let's get started, and we can think about level surfaces of 3D functions, which can be important with the quadric surfaces. Okay, so here's a definition for you. This is going to be a fairly long-winded one. Let's imagine that I have some surface defined by f of x, y, z equals k. So what we're doing is we are setting some output w equal to k. So this is going to leave us with a three-dimensional, with some sort of three-dimensional object that we're going to be left with. So if we imagine this graphically, we have some surface. Here's our surface. It's a really bad drawing of the surface, but okay, let's just imagine that this is a surface, right? Okay, and this surface is defined by some k. Now this surface can be a quadric surface, it doesn't really matter. Anyways, we set a point equal to p of x naught, y naught, and z naught. So that can be our point. And then what we do is we define some curve, some arbitrary curve on r of t, or some arbitrary curve on the surface. So here's our curve. So here's our curve C, some surface S. And this curve can be defined by a vector function. We parameterize it. So this is here vector R, and R changes based on the position. And we can parameterize it such that R of t equals x of t, y of t, and z of t. So by this definition, we can also parameterize our function on the surface so that f of x of t, y of t, and z of t is equal to k. Okay, so now what we're going to do is we are going to differentiate this. When we differentiate this, we need to use the chain rule, right? Because x, y, and z are all functions of t. So we get partial f partial x, dx dt, plus partial f partial y, dy dt, plus partial f partial z, dz dt, equals 0. And we can rewrite this as a dot product between the gradient of f with r prime of t. As you can see, we're adding each of the components, right? We've got 1, 2, 3, and then 1, 2, 3. Should be fairly self-explanatory. And of course, that's equal to 0, because when we differentiate k, which is a constant, we get 0. Good? Good. Okay, so now what we are going to do is we are going to put this in the context of our knotted points here so that we can actually use this. And that says that the gradient of f of x naught, y naught, and z naught times r prime of t naught is equal to 0. Now we can further rewrite this and apply this into our equations for a plane that we've determined back in earlier videos in Unit 1. And we can make this into a sort of plane equation. So when we do this dot product, so what we get partial f x naught, y naught, z naught times x minus x naught plus partial y f of x naught, y naught, and z naught times y minus y naught plus partial z f of x naught, y naught, and z naught times z minus z naught equals 0. Okay, this is very abstract, so why don't we try an example? This one shouldn't be too difficult. I would like us to find the tangent plane to x squared over 4 plus y squared plus z squared over 9 at equals 3 at the point -2, 1, -3. Okay, so what we're going to do first is we are going to assign this to a three-dimensional function. We'll let k equal 3 because we've got 3 here. Then, if we let k equal 3, then we can define a three-variable function, setting f of x, y, and z equal to x squared over 4 plus y squared plus z squared over 9. Now we can evaluate a bunch of partial derivatives at our given point. So we get partial f partial x equals x over 2. That's fairly simple. And then we evaluate partial x of f at -2, 1, -3, which yields -1. Doing the same for partial f, partial y, we get 2y. If I take partial y of f of -2, 1, -3, we get 2. Finally, if I take the partial derivative with respect to z, I get 2z over 9. And this means that the derivative here evaluated at -2, 1, -3 is equal to -2/3. Plugging this into the final equation that we saw in the last slide, we get -1 times x plus 2 times y minus 1 minus 2/3 times z plus 3 equals 0. And this is, of course, the equation for a plane. So we can see what this looks like graphically. We have, obviously, this is an ellipsoid, if you remember your quadric surfaces from earlier. But anyways, what we get is we get some ellipsoid, and we also get a tangent plane to this level surface here. Okay, so there's our tangent plane, and here is our level surface, level ellipsoid with horizontal and vertical traces of ellipses. All right, thanks for watching today's video. In the next video, I would like to open up the discussion to maxima and minima. As you are going to see, this is a far more nuanced topic than simply setting the derivative equals 0. There's a lot more guessing and checking that we need to do. So we'll discuss that in the next video, just as an introduction. And then we will be moving on to Lagrange multipliers to round off Unit 3. Thanks for watching. We'll see you guys in the next video. Bye.